quasi-linear preferences. So this is a kind of IC that we haven't seen before. Okay. Suppose that a consumer has IC that are vertical translates of one another. That is like this. Okay. What does this mean? This means that all of the IC are just vertically shifted versions of one IC. It follows that the equation for an IC takes the form x2 equal to k minus vx1. Okay, so I'll write it here. So x2 equal to k minus v x1. So here x2 is this height. Okay, x2 is this height. So we can say that this equation says that the height of each IC, height of each indifference curve is some function of x1. So that function is minus vx1 added with the constant k. Okay, higher values of k give higher indifference curve, definitely. Then, so these are vertical translates, and how will this horizontal translates look like? So it will be like, this won't be touching. Okay. So the horizontal translates as like this. Then this is this equation. All the equations have to be by hearted. Okay, this is the equation. So in this case, the utility function is linear in good 2 only. Most possibly, good 1 will be a non-linear. That is why this got the name quasi-linear utility. Then specific examples of quasi-linear utility would be u x1 x2 equals root x1 plus x2. Cool. That's it. Next is Cobb-Douglas preference. So this is how the graph looks like. And how we derive this. So for the first one, oops, sorry, we can't draw one though. So consider here we have a BMW car or BMW car, and here we have pen. So BMW car will cost this much, and how much will the pen cost? So for one this price we'll get this much pen. Okay, so it comes like this, and in the opposite, like pen here, BMW here, BMW here, then how it will be? So more for the BMW, less for the pen. This it will be like here. Okay, so this denotes A and this denotes B. Okay, so this is what Cobb-Douglas is. So this utility function will be useful in several examples. Like preferences represented by the Cobb-Douglas utility function have the general shape depicted as this. So we have illustrated the IC for C equal to half and D equal to half, and figure 4.5b we illustrated it as C equal to 1 by 5 and D equal to 4 by 5. Okay. So Cobb-Douglas indifference curve is the most well-behaved IC because it has convex monotonic ICs. Okay. Convex monotonic ICs present here. So they are the standard example for ICs that look well behaved. In fact, the formula describing them is about a simplest algebraic expression that generates well behaved preferences. So we'll find Cobb-Douglas preference quite useful to present algebraic examples of the economic ideas that we'll study later. Of course, a monotonic transformation of the Cobb-Douglas utility function will represent exactly the same preference, and it is useful to see a couple of examples of these transformations. So we'll take the formula, the equations, okay. This is how the equation looks like. So if you're getting confused with all these parts, so we are using logarithm here for this monotonic transformation. So if you're getting confused with all those parts, this is the final. Just go over this. So this means that we always take a monotonic transformation of the Cobb-Douglas utility function that makes the exponent sum to 1. Exponent sum have to be 1. Okay, two goods will be here. First good will be like A, then the other will be 1 minus A. So that's it with the preference examples, and next is marginal utility. So consuming some bundle of goods x1, x2, how does the consumer's utility change as we give him a little more of good one? The rate of change in this utility, satisfaction that the consumer gets from an addition amount of unit of good is known as marginal utility. Okay, so this can be calculated with this. Okay, so marginal utility will be change in utility by change in number of goods, unit of goods. So how can we denote the change in utility? That will be u x1 plus delta x1 minus x2, comma x2 minus u, the original utility, u of x1 and x2 by delta x1. Okay. So that is with the marginal utility. Then here we are just calculating the utilities of with respect to good 1 and good 2. So for good 1 we just calculated it in this above. So this is the change in utility, that is change in utility means marginal utility with respect to good 1. So how did the change in good 1, that is x1, when little more of units were added to x1, that is the change in x1. Okay, so how did the change in x1 influenced or impacted or affected the utility? So here the marginal utilities with respect to good 1 were in the next example, it is with respect to good 2. So both we use the same principles. Okay. And same equation. Okay. So it is important to realize that the magnitude of marginal utility depends on the magnitude of the utility. Thus it depends on the particular way that we choose to measure utility. If we multiplied utility by 2, then marginal utility would also be multiplied by 2. We would still have a perfectly valid utility function in that it would represent the same preference, but it would just be scaled differently. Preference will be same, but just the scaling will be different. Okay. So this means that the marginal utility itself has no behavioral content. We ranks different bundles of goods. So that is how we calculate the marginal utility. Huh? Marginal utility depends on the particular utility function that we use to reflect the preference ordering, and its magnitude has no particular significance. It turns out that marginal utility can be used to calculate something that does have behavioral content as well. That is in the next section, that is marginal utility and MRS. So, a utility function u of x1 and x2 can be used to measure the marginal rate of substitution. What is MRS? The willingness to pay. Okay, that is how much you are willing to substitute good 1 for good 2. That is MRS. The rate of this change and willingness is MRS. So the interpretation gives us a simple way to calculate the MRS. Okay, consider a change in the consumption of each good. Delta x1, delta x2. Change. Okay, so delta x1 and delta x2. That keeps utility constant. The change in each goods have to keep the utility constant. That means the utility derived must be equal to 0. How? The change brought by the utility in both goods will be calculated as per marginal utility of delta x1 and marginal utility brought by delta x2. That will be equal to delta u, and that will be equal to, that have to be equal to 0 if it have to move on the same indifference curve. See, change in consumption that moves along the same indifference curve. That means the utility have to be same. Indifference curve means what? And the same indifference curves means all the bundles on an IC have to get the same utils. So in order to satisfy that condition, here the utility marginal, not marginal, the change in utility have to be 0. So next is solving for the slope of IC. So okay, the slope is always like delta x2 by delta x1, and that here is minus mu1 by mu2. Okay, so the algebraic sign of MRS is negative. If you get more of one good, definitely you need to less good 2. The opportunity goes to, okay. So the MRS will be negative. It is tedious to keep track of the pesky minus sign because MRS is often referred to absolute value, that is positive number. Okay. So here there is nothing much important. Just read it. It is just speaking of this equally valid utility function. Like when we divide the utility by 2 or 4, whatever the ratio is not changing, right? Ratio of the marginal utilities give us an observable magnitude, and it is not changing whether we divide it with the same number. So that's it here. Then taking a monotonic transformation is just relabeling the IC, and calculation of relabeling the IC, and calculation for the MRS is concerned with moving along a given IC. Even though the marginal utilities are changed by monotonic transformation, the ratio of the marginal utility is independent. So that's what we discussed now. Next is utility for commuting. So I'll just read this. There is nothing much in that. Okay. Utility functions are basically ways of describing choice behavior. If a bundle of good X is chosen when a bundle of good Y is available, then X must have higher utility than Y. Okay. So this idea has been widely applied in the field of transportation economics to study consumers' commuting behavior. In most large cities, commuters have a choice between taking public transit or driving to work. Each of these alternatives can be thought of as representing a bundle of different characteristics like travel time, waiting time, out of pocket cost, comfort, convenience, and so on. We could let x1 be the amount of travel time involved in each kind of transportation, x2 the amount of waiting time for each kind of transportation, and so on. So if we go on a set with x1, x2 goes on until xn, it represents the values of n different characteristics of driving, and the same with y representing the values of taking the bus. Okay. So more specifically, let us suppose that the average consumer's preference for characteristics can be represented by utility function of the form okay. So the coefficients beta 1, beta 2 and so on are unknown parameters. Any monotonic transformation of this utility function would describe the choice behavior equally well, of course, but the linear form is spatially easy to work with from a statistical point of view. So this is a report of utility function, and this is not that important, but I'll give an explanation on that. So Thomas Dominic and Daniel McFadden, the urban travel demand. Okay, so this is a North Holland publishing company in the year 1975. The estimation procedure in this book also incorporated various demographic characteristics of the households in addition to the purely economic variables described here. Daniel McFadden was awarded the Nobel Prize in Economics in 2000 for his work in developing techniques to estimate models of this sort. So if you are interested, you can just read that part. This is their result of the report result. Okay, so next is this also goes with the explanation of the report. You can read that. So that chapter utility is over, and the review questions will be done at the end when we cover the whole syllabus of this semester. Thank you.